Hello, it's Mr. Morse, and we're looking at Cvpm worksheet number 3. We're focusing on position and time graphs, and we are trying to figure out what we can learn by looking at those. So in number 1, we're looking at a person roller skating down a sidewalk, and we have positions and times. So we're going to start by working on this graph. I'm going to zoom in a little bit, or maybe a lot, I guess, to make the graph a little bit easier for me to draw. We've got it right there. And let me pull out my drawing tool. There we go. We need to number this axis. So I'm going to make each box 2 seconds going across. So let's see, 2, and then 4, and then 6, 8. We only go up to 10 seconds. Although that doesn't use the whole graph, it goes over half of it. On the y-axis, where we're going to put position, I'm going to make each box 5. It would be totally fine to start at 10 meters, but this will give us a slightly better idea of where our intercept is hitting. So we have a time at 0. Our position is 10 meters. Sorry, at 1 second, we're slightly above that at 12. Here at 2, we're almost up to 15, so we're right below that line. At 5 seconds is our next piece of data, is when we find ourselves up here at 20. Next, at 8 seconds, we're up at 26, so a little bit past that line, and 10 seconds, we're at 30. So we don't have perfect dots there, but pretty good, and I can make a best fit line. Okay, I did not have a straight edge, so we will do our best with that. So then we're going to unzoom that. We see a position versus time graph for the skater, and it looks pretty decent. A fairly straight line with a y-intercept right at 10 on a position. Then we're asked here, how can you use the graph to determine how far he was from the origin at 6 seconds? So we look at our data. We've got 5 seconds. We've got 8 seconds. We don't have 6. So we don't have anything there, but we could estimate between these points. But even better, the reason we make graphs and the reason we'll see down below that we're going to be making equations is that so we can answer those sorts of questions. So if I come over, right here is 6 seconds, and then I scoot up, I see that I'm a little bit above 20. And I can estimate that I'm kind of in the 21 to 22 range. So I get a pretty good estimate from that, knowing that I'm between 20 and 25, closer to 20. And if I had a really nice best fit line there, I could get a really nice estimate. So then we're going to scroll down a little bit. Okay, that moved that. I want to move, there we go, that. Write the mathematical expression that describes the skater's motion. So we're going to zoom in again here, and we're going to we are going to reword that. So mathematical expression, let's cross that out. Let's write something here that you've seen a lot in class. Write the physics equation. So hopefully that's not a surprise that I was going to write that there. So write the physics equation that describes the skater's motion. So equation, we've got a straight line there. That means y equals mx plus b. But we don't use y's, we don't use x's there. We think about what each of those means, but we do need our m. So we're going back up to the data. You can look at it. All of our points are right on the line, so I'm going to use a y, the 10, 30. Sorry, the time at 10, the position is 30. Then I can subtract, let's see, maybe one of the earlier ones, 12. So when we were at 1 second, our position was 12, so I've got 18 over 9 here, and I get an m that has a numeric value of 2. And that may have been cut off, 2. And then we do think with slopes always, what does that mean? Well, the units on the y was meters, the units on the x was seconds. So now we're ready to turn that into a physics equation. Our y was the position. Our m we just wrote down was 2 meters per second. The x on this is time. And then plus b, we saw very clearly on our graph that at time equal to 0, our position had a value. It was 10 meters. So we have a physics equation. Position equals 2 meters per second times time plus 10 meters. And then as we're answering our next question here, was the speed constant over the entire interval? Well, we're thinking speed, or velocity would also work here, but speed is the distance traveled over the time, and yes, it was constant. We had a straight line. That straight line had a constant slope. So that's what we're looking at there. As we go on to the next, here we are on the second page. We still have a skater. We've got some new data. So we're going to plot that, and then we're going to be able to do a lot of the same ideas. So let's start by zooming in so we can make a decent graph, and then answer some questions from it. So this time, numbering the axis pretty similarly, 2, 4, 6, 8. So I'm going to skip 4, 6, 8, 10, 12, just so I don't have to write as much and it's not quite as ugly. And then we'll do 5, 10 again, 15, 20, 25, 30. You notice that I did not label my axes here, and that's because it's already been done for us. Time in seconds, position in meters, and it would be good here if we did do a title just to remind ourselves what we are doing or to be in practice of that. It's kind of ugly, but position versus time, or y versus x. So now we're ready to drop some dots on there, so I'll get my nice big pen mark here. At time equal to 0, we are now at, right there, 4 meters. At 2 seconds, we're up to, missed it, 10. At 4 seconds, there we go, we are at 16. 6 seconds, we're up to 22. 8 seconds, we are up to 28. And 10 seconds, we are at 34. And now let's try a best fit line, which you see how hard it is for me to just write numbers here. So you're forgiving the fact that that's not that pretty. But we zoom back out and we have a line that you can almost see looks decent. Plotted it, so A is done and good to go. How far from the origin was the skater at t equal to 5? So we know that here it's somewhere between these, but we go right there, there's 4, there's 6, so we go up. My line is really bad when I look at it, so bad that it is bothering me, and I am going to zoom in. I am going to change to a red pen. I am going to try my best to actually, there we go, make one that goes through all of them. Slightly better. Hopefully we wouldn't have that problem with the straight edge, but at 5 seconds we go up, and we're almost at 20. So maybe we're at, excuse me, about 19 meters there. The how do we know? We go over to the time on this axis, we go up, and then we see where it connects over there. So let's see, scoot, scoot, scoot. Was the skater's speed constant? If so, what was it? So yes, it was constant once again. We have a straight line with a constant slope. In this case, once we got around to having a decent line on there that I was able to draw in red, we saw the data points did fall right on there. And change in y over change in x is our slope. 34. It was at 34 meters when we were at 10 seconds, so that's an XY pair. Choosing an earlier one at 2 seconds, we were at 10 meters, so we had 24 over 8 or 3, and it's always important to think about what these numbers mean. That's 3 meters per second. So we're now comparing the two different trials. In the first trial, the skater was further along at 2 seconds than he was in the second trial. So you can flip back over and see that the first trial we were at 14 meters. This time we're only at 10 meters. Does that mean he was going faster? Explain your answer. The answer on that is no. That just means at that time he was had a larger position. Could we explain or answer it specifically? Well, we had the slope in each case. This time it was 3 meters per second. The previous time it was 2 meters per second. So that would be some great evidence to use for that. The other piece of that is just thinking about our intercepts. Here at time equals 0, we were at 4 meters. In the previous one, we were at time equals 0, we were already at 10 meters. So in question 1, the reason the skater was further along at 2 seconds was that he was way further along at 0 seconds. So thinking about the slopes, thinking about our intercepts, those are great pieces of evidence, and then we can connect that with an explanation. And here we are on to question 3. Now we have a skater observed with all of these data points. We're going to start by plotting the position. You're used to my zooming and making weird noises. You're used to my bad handwriting by now, and we're getting used to it. As we look at the times here, this one's actually going to fill it. So we're going to go 2, then 4 seconds, 6, then 8 seconds, 10, then 12 seconds, and this last one would be our 16. So we've got our times there, and as I go up, this time we don't go quite as far, so I am going to just go 1, 2, 3, 4, 5, 6, 7, and then that's going to be my 8 meters. Now, as I'm ready to plot my data, I have a little bit more, and this time we do start at the origin, so we've got a 0, 0. At 2, we're at 2. All right. At 4, we're at 4. That's easy. But then at 6, we're still at 4. At 8, we have come back to 3. At 10, we're back down to 2. At 12, we are still at 2. At 14, we're all the way up at 5, and then we end at 16 up at 8. So that is obviously not a straight line that we're going to try to connect with just one best fit. What we're going to do is we're going to connect kind of some line segments here. So we've got this, 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 and right there. So straight edge would have been awesome, but here we are, all the technology in the world, and I can't draw a straight line. But you get the shape of the graph there. We have a straight line with a positive slope, a straight line that's horizontal, a straight line with a negative slope, another horizontal section, and then another straight line with a positive slope. And we're asked about some of these sections. So what's happening right there from there's 4, there's 6. So I described we had a horizontal slope right there. Well, that means at 4 seconds, at 5 seconds, and at 6 seconds, our position has stayed the same. So in that instance, our skater is staying still or has stopped. We described our next section from 6 to 10. It's a straight line with a negative slope. So starting at 4 meters, going to 3, going back to 2. Well, that skater's still traveling at constant velocity, but traveling at a constant velocity back towards the origin, or maybe in the negative x direction would be another way of saying that. So it's a negative slope because we're traveling in the negative x direction. We've got 2 different calculations we're going to be doing here, looking at D and E, and then that leads into questions 4. Determine the velocity, remembering that velocity is displacement divided by time, and then speed. So 2, what so many people use as interchangeable words, but aren't really the exact same here. So we've got velocity is our delta x over our delta t, or it's better to use those in terms of the physics terms, our change in position over change in time. Final position minus initial position, we end at 8. We started at 0. We end at 16 seconds. We start at 0. 8 over 16, we've got 1 over 2. It is meters per second. Velocity does have not just magnitude, it has direction. This time, because we've defined, our direction in terms of positive versus negative x values, the fact that this is just positive 1/2 does give us that direction. Now, as I look at E to get to speed, speed's different. It's distance or path length. So I would even call that, I like saying total distance when people get a little confused by the word path length. And apparently I like reading it illegibly, but total distance over time. So when we do that, we need to not just, and I will scroll back up here, not just think about where we're starting and where we're ending, but look at the path. Well, we went along here, we stayed still, came back, re-traveled some distance we already went, and then kept going. So as we're looking at total distance, the skater went 4 meters at first in that first segment and then stayed still, and then did come 2 meters back. Well, that was distance that was traveled. It doesn't matter which direction it is total distance. Then stayed still, then went 6 more meters. All of that still happened in the same amount of time. So that's a total of 12 over 16, or a little bit faster in terms of the speed. Yikes, sorry, 3/4 meters per second. So you can't read what I have here. It kind of holds you accountable that you have to watch the video. In what situation might speed be a better motion than average velocity, when velocity might be better than speed? And I hear kind of some sarcastic answers here where people say, well, velocity is good in physics class, but speed's good everywhere else. But an important thing with speed is that we're looking at total distance here. It doesn't matter where we're starting or ending. So if you're running a race, depending what race you're running, or if you're driving in a race, we've got the Indy 500 here. We're going round and round and round in circles, we know. Well, in that, the starting line and the finish line is pretty much all the same place. So speed, it doesn't matter where you started relative to where you ended. As you go around that circle, we want to know how far did you go. So that's a good total distance over time scenario. Whereas velocity, if you're going around in a circle over and over and over, your velocity is going to be 0 when you end at the same place you started at. So maybe something more like a plane flight would be a great one. That's probably my best scenario that everyone's thought of there, because it doesn't necessarily matter to us, did our flight take the shortest possible route or the most direct path, or what exactly was the path? I guess that's what I'm getting at. But from where I started to where I end, how far did I travel? And then how much time did I take? So that's a good one. Both of them are giving us similar information, but there is a difference there. And here we're finally getting to the back page. We've got 6 graphs here, and we're asked to rank them in terms of velocity, and we're asked them to rank them in terms of speed. So we want to see what's the same, what's the difference, and we want to explain our rankings on each of these. So what we want to do is look at how much position or distance has been covered in each case, and then what is the speed. So I'm going to do everything related to average velocity in red. So my change in position over time here is 0 over those 10 seconds. It was a really high line, so that may have led you to believe it was going to be faster, but it's no change in position. Right here, I'm also have no change in position over those 10 seconds. Right here, I start at 0, I end at 10, so I went 10 meters in 10 seconds. I have 1 meter per second. Here, I went from 3 up to 10. I went 7 meters in 10 seconds. Here, I went from 15 down to 0, negative 15 meters in 10 seconds. Let's write the 10 there. And then right here, I am not caring about my path length. Where did I start? Where did I end? 5 meters of displacement in 10 seconds. So now I've got some different values here. I've got 10 tenths or 1. I've got some 5s, 15 zeros. So the most positive was C, 1 meter per second. The next one is D, 0.7 or 7 tenths. Remember, all of these have that same unit of meters per second. The next one would be a half of a meter per second, so F. We've got a couple tied here. We will say 4 and 5 are tied, or I'm going to put them even both at 4 so that it's clear that one is not above the other. A is equal to B, And then, because we were looking at most positive to most negative, E, even though it had the most displacement, velocity has magnitude, but it also has direction. So that one's the most negative. So as we are looking at this, we're doing a couple things. We're looking at displacement versus time. But as we explain our reasoning, nobody wants to read my handwriting of a long paragraph here. So we're going to kind of highlight some things that we are looking at. We're looking positive versus negative. That's important. We're looking at our change in X. And we're looking not just at the steepness of the lines, extra S for good measure, yikes, that was embarrassing, but we are also looking at the labels, the units, the spacing, the actual numbers on that. Just because I do want to say, wow, look how steep this one looks, but that one, once we start to get into the values, is a little bit better and cleaner. So I'm going to clean all that off and then look at speed. So I cleaned all that off. Now I'm going to be changing to blue as we look at, and let's scoot just a tiny bit, speed. So we still have the same idea, but speed is total distance. Well, we still travel 0 total distance, 0 total distance. Here we're looking at 10 meters per 10 seconds, 7 meters per 10 seconds. Here it's still negative 15 meters per 10 seconds. But that negative is not going to be important here because we're looking not at it in terms of change in position so much as just how much distance was covered. So that negative, although that is the direction, does not matter. And then here on F, it's a little bit different. We've gone up 10. We've come back 5. So we have traveled 15 again. These all do have units still of meters per second. But as we rank these, the average speed, we're going to see the greatest. We've got E. I forgot my equal to sign there, so let me click back. Undo a couple things. The eraser's not working great today, but E equals F. And then C is next, D is next, and A is still equal to B. So with speed, some differences that were important as we explain our reasoning is that the magnitude is important, not the direction. So that's why that being negative doesn't matter. We also have positive. We're not looking just at the displacement. We're looking at how far we've traveled. And then we still have our zeros, and then we're looking at our other values here. So those were some important things. When we're answering these, we've got our PEE acronym, our point, what's the answer? The evidence is, let's get some specific things off the graph. And then the explanation would be where we connected maybe here, talking about that we're just looking at the difference in position, whereas down here we're looking at the total distance. Here we are looking at positives or direction in addition to our magnitude, whereas down here that does not matter. So if you missed anything, if it didn't make sense, go back, watch that part of the video, and ask some questions.